We continue with radical expressions, and we talked about simplifying some in the previous lesson. We're going to talk about a new element of it in this one. So to be fully simplified, no radical sign can remain in the denominator. So it's fine to have a radical sign, square root, cube root, whatever, in the numerator on top, or by itself if it's not a fraction, but it cannot be in the bottom of the fraction. It cannot be in the denominator. So to get rid of the radical in the denominator, we must rationalize the denominator. So on number 1, for example, you see we have the square root of 10 over the square root of 2. So the way we can get rid of the square root in the denominator is by multiplying the top and bottom by the square root of 2. Because we can, when we multiply, combine things that are both inside the square root. So 10 times 2 is 20, so we have the square root of 20. The square root of 2 times the square root of 2 is the square root of 4, which is 2. And that's going to happen every time you multiply a square root by itself. If you notice, essentially it just makes the square root disappear and you keep the number that's inside. So the square root of 2 times the square root of 2 is 2. We do need to simplify this on top though, like we learned before. We need to look for a perfect square that's a factor of 20. So we could rewrite this as the square root of 4 times 5. The square root of 4 is 2. The square root of 5 is 5. And often we'd be done at this point. But in this particular example, we have two things outside the square root that can be reduced. 2 divided by 2 is 1. So we end up with an answer of just the square root of 5. Okay, on number 2, I'll give you a hint. What we could have done to make it a lot faster on number 1 is notice, wait a minute, these are both inside square roots. Just like I can multiply two things inside square roots, I can also divide two things inside of square roots. So you could say, well, 10 divided by 2 is 5, so the answer is the square root of 5. I'm sorry to say not all of them go that fast or can work that fast. This one could. But in general, it will take the steps we did here, which is why I did the longer way to show it to you. So in number 2, we will look first and say, let's reduce before we rationalize the denominator. So these are both divisible by 5. So I can say 5 divided by 5 is 1. And you can just say 1 because square root of 1 is 1. 10 divided by 5 is 2. You do have to keep the square root in that case. So we really have 1 over the square root of 2. So just like we did on the previous example, we'll need to multiply the top and bottom by the square root of 2. Square root of 1 times square root of 2 is the square root of 2. The square root of 2 times the square root of 2 is the square root of 4, and the square root of 4 is 2. Okay, we'll see something similar here in number 3. We have a square root in the denominator, so we need to rationalize to get rid of it. To do that, we multiply the top and the bottom by the square root of 3. On top, we cannot combine these two. You cannot say this is 12, because this one's outside the square root, this one's inside the square root. So we just leave it as 4 times the square root of 3. But down here, square root of 3 times the square root of 3, that's the square root of 9, which is 3. Okay, on number 4, we can simplify before we rationalize. Those are both divisible by 5. 35 divided by 5 is 7. 15 divided by 5 is 3. And square roots, when we're dealing with fractions, square roots mean the same thing whether they are over the entire fraction or just over the individual parts of a fraction. So if it helps you think about the rationalizing to split it into two pieces, by all means do that. So then we multiply the top and bottom by the square root of 3. These are both inside the square root, so we can multiply 7 times 3 and get 21. The square root of 3 times the square root of 3 is the square root of 9. And the square root of 9 is 3. And again, make sure you don't simplify when we're not allowed to, because we cannot simplify this. I'm just going to rewrite it down here so it's more visible. But we cannot simplify this because even though 21 and 3 are both divisible by 3, 21 is inside of the square root, 3 is outside the square root, and we can't mix those together or reduce them when they're not both in or both out. Number 5, we'll reduce first. These are both divisible by 15. 15 divided by 15 is 1. 60 divided by 15 is 4. Those are both perfect squares. Square root of 1 is 1. Square root of 4 is 2. So we did not have to rationalize that one because it turned out that they were both perfect squares. But we can only see that once we reduced. Okay, number 6. I'm going to go ahead and write it as 2 separate radicals. We got to get rid of the square root of 7, so we multiply the top and bottom by the square root of 7. 5 times 7 is 35, and we can combine those because they're both inside the radicals. Square root of 7 times square root of 7 is the square root of 49, and we know the square root of 49 is 7. So when you are asked to simplify radicals, you have to remember that even if you can simplify the fractions like we did here, you still have to rationalize it to make sure there are no radicals left in the denominator. You cannot have a final answer with a square root in the bottom of the fraction. Okay, now we're still talking about radicals on the back of the page here, but we're not talking about simplifying them. We're talking about combining them. Just like with variables, we had to make sure they are alike. We have to do the same with radicals. So x and 8x, those are like terms or like variables. 4m and 5m are like variables. So these are like radicals because they both have a square root of 3. These were like variables because they both have an x. So their coefficients can be different. That's a 1x and an 8x. That's a 1 square root of 3 and a 5 square root of 3. So the coefficients can be different. But just like the variables have to be the same, what's inside the radical has to be the same. So just like these are unlike variables because the letters are different, the variables are different, or in this case, the exponents on the variable are different. These are unlike radicals because here it's a 3, here it's a 5. And even though both of these have 5, this one also has an x. So to be like radicals, they have to be identical inside. Okay, so let's look at number 1, because the first thing we need to consider, well, I guess the first 2 things we need to consider is, can these radicals be simplified individually? I know the instructions simplify, but they're saying simplify these 2 terms together. I'm saying as we look at each one individually, we say, okay, can that be reduced? Nope. Can that be reduced? Nope. Well, if we want to be able to add these together, they have to be like radicals, which these are. They're both the square root of 2. This is saying you have 5 square root of 2's, and if you add 7 more square root of 2's, you just say 5 plus 7 is 12. So you end up with 12 square root of 2's. Okay, these both are like radicals. They both have a square root of 7. So we can just simply subtract and do 6 minus 3 is 3. We did have 6 square root of 7's, but we took 3 of them away, so now we just have 3 left over. But of course, because it's my job as a math teacher, it gets a little bit harder. Here, we notice, this is why I mentioned on here, you have to see if they can be reduced. Because these are not like radicals. So I need to see if they can become like radicals when I reduce this. So we got to think, okay, what factor of 18 is a perfect square? That would be 9. So we can rewrite 18 as 9 times 2. And then with 50, is there a perfect square that's a factor? And that'd be 25 and 2. The square root of 9 is 3. The 2 stays inside because it's not a perfect square. The square root of 25 is 5, and it stays inside because it's not a perfect square. Now that we've reduced them, they are like radicals, and we can combine them. There's 3 of them here, plus 5 more of them here, for a total of 8 square root of 2's. We'll do something similar on number 4. These are not like radicals, but we need to see if they can be reduced. Now, whether or not they can be reduced, if even after reducing, they're not like radicals, then you would just leave it as it is. So let's just pretend for a second this had turned out to be 5 square root of 3. If that was true, this was 5 square root of 3, these would not be like radicals because what's inside them would not be the same. So your final answer would just stop here. Excuse me, stop here. But since they were like radicals, we could go one step further. Okay, so on this one, we need to think what factor of 12 is a perfect square. That'd be 4. Same with 48. We got to think what factor of 48 is a perfect square. Well, 4 does go into it, but a bigger one, which is 16. And if it's needed, you can write out the factors over to the side just to help you think through it. You can say, okay, I've got 2 and 24, 3 and 16, 4 and 12, 6 and 8. So you notice there's actually 2 perfect squares that show up. When more than one perfect square shows up, you do need to choose the biggest of them. Otherwise, you'll have to reduce twice, and you don't want to do that. So I'm just rewriting this 4. Square root of 4 is 2. The 3 is not a perfect square, so it stays inside. Just rewriting this 6. The square root of 16 is 4. That 3 is not a perfect square, so it stays inside. Now we do need to multiply these together because this is all multiplication. This is really 4 times the square root of 4 times the square root of 3. But I know the square root of 4 is 2. So I get 4 times 2 is 8. 6 times 4 is 24. So I get 8 square root of 3's minus 24 square root of 3's. So I'll end up with a negative because 8 minus 24 is negative 16. So it'll be negative 16 square root of 3. Okay, and the last thing is how to multiply them, which in this case we will be using the distributive property. So 3 square root of 5 times 2 square root of 5. So we've talked about this before, but I got to make sure I drive it home. When you're multiplying and dividing, you can only combine things that are either both outside the radical, like the 3 and the 2, or both inside the radical, like the 2 5's. So I can say 3 times 2 because they're outside the radical and get the 6. I can say 5 times 5 because they're inside the radical and get 25. Then I multiply it by this one. So I have the 3 outside times the 5 outside for 15. The 5 outside times the 3 inside to get the square root of 15. Now these are not like radicals, so I cannot just add them together. But we need to see if there's anything that will let us to reduce it. Well, if we see this right away, square root of 25, we know, because it's a perfect square, is 5. This cannot reduce, because the only factors it has are 15 and 1 and 3 and 5. Neither of those are perfect squares, so nothing will change on this one. So 6 times 5 is 30, but the second term gets left just the way it is. So this is like what I was trying to warn about earlier. There are times you can reduce, because we were able to reduce that just to 5, then do 6 times 5, but they still were not like radicals, so our final answer had 2 terms, and that's okay. Okay, number 6, same idea. We'll distribute. 5 on the outside, 3 on the outside. 3 on the inside of the radical, 2 on the inside of the radical. then there's an understood 1 out here, so 5 times the 1. Then square root of 3 times square root of 3 is the square root of 9. So we again end up with a perfect square. We can't reduce this one, but square root of 9 is 3. So we can get 5 square root of 6 minus 15. And that's as far as we can go because they are not like radicals. One has a radical, one doesn't. And so since the radicals aren't identical, that's our final answer.